Welcome everyone to NSTA Web Seminars, where you can find live interactive learning at your desktop. Tonight's presentation is part of our series on preparing for the next generation science standards, and tonight's focus is on the practice of constructing explanations and designing solutions. Our presenters tonight are Katherine McNeill and Leema Berland, and we also have Ted Willard, NSTA's Director of Efforts around the next generation science standards, online with us as well. My name is Bryn Slates and I will be moderating tonight, and Jeff Lehman is here at NSTA headquarters to provide technical support. I'll remind everyone that you can visit the NSTA Learning Center to find over 10,000 resources for science educators, and over a third of those are free. You can add these resources to your My Library area to access when it's convenient for you. We encourage you to check out the community forums to have discussions with your colleagues and other teachers across the country. And do take advantage of our online advisors who are there to help you find the resources that you need. Also check out our free tools for planning and documenting your professional learning. And it's all available by going to learningcenter.nsta.org. At this point, I'd like to turn it over to Ted Willard. Welcome, Ted.
Thanks, Bryn. Thank everyone for being here on what I'm sure is a busy week for all of you. I'm going to start off with just a few moments here, giving a sort of setting of the stage about the standards, and then let Kate and Leema talk about the practices they're focusing on. First step here is to understand the standards are an effort of 4 organizations working together: the National Academies, the Achieve, the NSTA, and the American Association for the Advancement of Science. So there is a sort of a 2-step process here in the standards. There was development of a framework that was done by the academies back in 2011. And the standards themselves, which are being worked on, coordinated by Achieve, working with a group of 26 states. You can see the specific ones listed there in blue. I'll take a moment to note that just because these states are working on the development of standards does not mean that they are definitely going to adopt them. They will make that choice once the standards are completed. And the states that aren't involved in the process also will at that point have a chance to make a decision about adopting them. But these standards then will lead to assessments, curriculum materials, instruction, teacher, professional development, teacher education, all the elements that are necessary to develop an education system to achieve the standards. As I said, the process is currently going on. A first draft was released back in May, and I think you probably all know that we are awaiting a second draft that was is expected, I think, coming soon is the best that I can give you. I know there'll be a notice of a couple weeks before the draft is released. We've not received such notice yet, so you can all rest assured and go and do your holiday traveling and not have to worry about, the standards coming out while you're on vacation. And as soon as NSTA has a date on that, we will make sure that you are aware of it. The framework, as I mentioned before, was released in 2011, and it was done by a group that included scientists, including a few Nobel laureates, and science educators. There are 3 dimensions that are emphasized in the framework: the scientific and engineering practices, cross-cutting concepts, and disciplinary core ideas. If you're interested in getting that framework, and I would highly recommend that you take a look at it. You can get a free PDF of it from the National Academies Press. You also can order copies of it through NSTA Press. So these are the practices that are mentioned here. We've gone through in our wet series through 5 of these so far. We're up to tonight constructing explanations for science and designing solutions for engineering. And we'll be in coming weeks, by the end of the year, we'll hit the last 2. Cross-cutting concepts as well are an important piece here, another one of these dimensions that the standards talks about. The list you can see here describes them all 7 of them for you. And then we've got our core discipline areas: life science, physical science, earth and space science, and then What's also been incorporated into the standards is engineering and technology. And under each of these pieces, you can see specific subcategories in terms of the architecture of the standards. And so this is what it looks like when you start to put all of this together. You can see here we have a performance expectation that is a mixture of different elements here. It has construct and use models to explain. So this is the practice of developing and using models to explain that atoms combine to form new substances of varying complexity going on here that deals with the structure and properties of matter, one of the disciplinary core ideas. And then we have this idea of the atom, sometimes there's repeating subunits in the atom, and this is an example of a pattern that you can find in science. There's these combine together and describe what is to be assessed. They're not, however, instructional strategies or objectives for a lesson. And so with that in mind as a backdrop, let's turn things over to Kate and Leema on constructing explanations and designing solutions.
So this is Kate McNeill. I just want to thank you guys again for joining us this evening. So what Leema and I are going to do is we're going to be talking about both constructing explanations and designing solutions. We just wanted to give you first a little sense of who we are. So as I said, my name is Kate McNeill. I'm a faculty member at Boston College. Before going back to get my PhD, I was a former middle school science teacher, and when I was a middle school science teacher, I became very interested in scientific inquiry. So I ended up going to the University of Michigan to get my PhD, and I ended up focusing on inquiry. Specifically, that turned into focusing on two specific practices, explanation and argumentation. And today we'll be talking a lot about explanation. Leema?
Thanks, Kate. I'm Leema Berland, and I'm a professor at UT Austin. I got my PhD in learning sciences from Northwestern, and I've been, similarly to Kate, been working a lot on supporting and understanding kids as they construct explanations and engage in argumentation. I've also been working more recently on the engineering side of things, and so I'll be talking a little bit about that today, too.
I think one thing I want to say as we start here is that the practices that we're talking about today are not easy. So these are things that students can have challenge with in a number of different ways. So what we want to talk about is kind of what are they, what challenges can kids have, and then how can you as educators help support them in that. And we've both had the privilege of working with some amazing teachers in different areas of the country. Recently I've been working a lot with the teachers in Boston. So we're going to be sharing examples from the teachers and students that we work with to kind of illustrate what these practices look like and how to support kids in them. We do have a caveat before we start our presentation here, and that is we are not the authors of the frameworks or the next generation science standards. So we are trying to interpret them here as closely as we can and use examples from the work we've done with teachers and students to illustrate that. But we didn't develop them, and we don't know what the next version is going to look like. So we don't have any, magic insights in terms of that, but we want to share with you our thoughts around them. Also, both of our primary expertise is in scientific explanations rather than engineering modeling. We both have done some work around solutions, and we're going to share that. But I think we feel like we have a richer set of expertise around explanation. So we'll answer your questions to the best of our ability. But just in terms of the work that we've done, we wanted to share that. So this is an overview of what we'll be talking about. We're going to start off by talking about the importance of explanations and solutions. Then we'll go into looking at some of the language and the framework in the next generation science standards. We'll talk about defining explanations and solutions. What do these practices really look like? As well as the relationship with the other 7 practices. Then we'll stop and give time for questions. And after that, we'll go into some examples. So we'll share some student examples from elementary, middle, and high school for both explanations and solutions, and talk about kind of what the students were doing there and what challenges they had. We'll again stop for questions, and then we'll talk about supporting students. So different strategies that teachers can use to help kids with these practices. And then again, another point for questions. So we'll have 3 different time points to stop for questions during the presentation. So we do want to start with a poll, and I want to emphasize this is not a trick question. There's no right answer here. I think all of these choices are actually good reasons to engage in it. What we're interested in is what you see as most important. So the question here is, what do you see as the most important reason to include explanations and solutions in K through 12 classrooms? So which of these do you feel like is most important? A, to have students share their own ideas. B, to help students make sense of the world. C, to support students in using evidence. Or D, to engage students in core disciplinary ideas. So if you could select which one is most important to you, we just kind of get a sense of what people are thinking here. It's interesting watching the numbers change. I see Ted has voted as well. So we have a lot of people picking B and C, as well as some A and D. Great. Bryn, would you be able to pull up the graph? I don't actually remember how to do that.
Sure thing.
All right, so if we see here a graph of the folks that voted, it looks like B was our most popular choice to help students make sense of the world. And then C came in terms of to support students in using evidence, with some folks picking A and D as well. That's great. So like I said, I think all of these are important. So if you look into the frameworks and the language around it, they talk a lot about how constructing explanations and designing solutions are key practices of both professional scientists and engineers. And engaging students in these practices can really help them understand how knowledge is constructed in both science and engineering. And we also think that developing these practices can help students become more critical consumers of the products of science. So we'll use this language throughout the presentation. This idea that the explanations and solutions are the products of what scientists and engineers are creating. So we want students to be critical of these, both if they end up in a science field themselves, but also if they don't. This is something that's important for all individuals to be able to do. Other reasons that it can be important is that engaging in these practices can absolutely help kids develop a more in-depth understanding of the disciplinary ideas of science. It can help them understand these core concepts in more detail, because they're using these concepts to make sense of the world as they construct explanations and designing solutions. So actually using these ideas can help them develop a richer understanding of it. There's also this idea that the focus on using evidence is a 21st century skill, that you use evidence in science, but you also use it across the domains in other content areas such as history, language arts, mathematics, as well as outside in your everyday lives. So this is something that we want students to be able to do, to be able to construct a claim, support it in evidence, critique claims constructed by others, both in the school setting and outside of the school setting. So what we have here is we took some of the language from the Next Generation Science Standards, from the May draft that Ted mentioned before. And if you haven't looked at it, there's a table that goes along with it, which I find very useful. So they have tables that have the different practices, and they articulate what those practices look like across K2, 3, 5, 6, 8, and 9, 12. So this is the language from that table around the practice of explanation. And it says the products of science are explanations, and the products of engineering are solutions. Specifically, explanations in science. The goal of science is the construction of theories that provide explanatory accounts of the world. A theory becomes accepted when it has multiple lines of empirical evidence and greater explanatory power of phenomena than previous theories. So there's two main ideas that we see here. One being how or why phenomena occur, and the other, this idea that it's relying on evidence. So here we have 3 sample explanation performances that we selected. And we selected these in order to cut across elementary, middle, and high school, and to illustrate these 2 themes that we see going on. This one idea in terms of explaining how or why phenomena occur, and this other idea around using evidence. We also selected these because we wanted to cut across different content areas. So the first one from elementary is from earth science. The second one for middle school is for life science. And the third one from high school is for physical science, specifically chemical reactions. So if you read the language of these, you'll see that in each case, the students are trying to make sense of the world around them. They're trying to understand how or why something is occurring, and they're specifically using evidence or data in order to do that. And when we look across the grade levels, what we see happening is, in terms of the phenomena, the nature of the claim is changing. We see in grades 3 through 5 a simpler claim, one which doesn't have as many variables in terms of explaining what's happening. And then when you get into high school, you get more claims that are about systems. They're bringing in more different variables, and they're becoming more complex to really understand the phenomena. The other thing that we see occurring is the use of evidence. This connects across from elementary, middle, and high school, but the way the evidence is used, it becomes more complex. In grades 3-5, it just says identify evidence that supports an explanation, versus in high school, it says apply scientific reasoning, theory, and models to link evidence to claims and show why the data are adequate for the explanation. So that becomes more complex as well.
So the other practice that's part of this is the constructing of solutions, kind of the more engineering side of things. And again, we want to emphasize the language that we're seeing throughout the framework, which is that science and engineering are driving towards these products of an explanation or an engineering solution. So specifically for engineering, the solution, they define it by saying the goal of engineering is to find a systematic solution to problems that is based on scientific knowledge and models of the material world. And then the optimal choice depends on how well the proposed solutions meet criteria and constraints. And it's this aspect that, that connects it to the explanation language around evidence, that here we're trying to solve a problem, which could be seen as parallel to constructing an explanation, and the solution needs to be based on how well your solution or your possible solutions are meeting the criteria. And so that would be seen as more as the evidence component. It's the evidence of the performance that it's meeting this pre-specified criteria. And the criteria in the engineering world can come from user needs, it can come from constraints, requirements, things like that. We're going to see some examples later on in the talk of different sorts of solutions, but I want to just mention quickly that it varies widely from what you might be imagining, a physical product that students are building, to sketches or paragraphs describing things depending on what the problem that's being solved is and the context. Sorry, remember how to move forward. So some sample performances around solutions include things like at the elementary level, you know, using magnets to move an object, and then moving through to high school where we're talking about designing something to create or maintain sustainability for local ecosystems. All of these, unlike with the explanations where we saw a really clear progression that was laid out with specific things like the claim becoming more causal and more variables coming into the picture, that is less clear currently in the framework for how the solutions will progress. Instead, I think the progression seems to be around the content of what they're designing solutions for. So we wanted to talk about where explanations and solutions fit with the 8 practices, with the 7 other practices. And I'm sure if anyone has been attending the other talks, everyone has a different representation of this that foregrounds their practice. Kate and I keep coming back to this language that explanations and solutions are the product for science and engineering. And with that in mind, we see them as the outcome. So you're using the other 6 or 7 practices to construct an explanation coming out on the right. you'll see put engaging an argument from evidence in the box with constructing explanations and designing solutions. And that's because, as Kate was highlighting, so much of the work around explanation construction is around using evidence to construct your explanation or to design your solution, and then defending and talking about why that's happening, or why your explanation is plausible. So they're really, they work together quite a bit. And we wanted to put up a big quote coming from the framework to kind of underscore this idea that explanation and argumentation are really working hand in hand and kind of happening in parallel. This is a long quote, but the gist of it is that we really, as we're developing an explanation, we're improving upon them through this process of argumentation, by justifying our explanations with the evidence, by comparing different possible explanations and evaluating those possibilities. That's how we identify strengths and weaknesses, and as it says here, it's how we figure out why the wrong answer is wrong, to develop a deeper understanding. And so we see these practices as really happening in parallel. And in fact, in practice, it often happens that we'll get a single product, the explanation and the argument wrapped up together, and that's how the framework is often talking about it and how we'll continue talking about it today. This slide I wasn't expecting. So the next slide is about your questions. I think that's our introduction to these two practices, and so Bryn has some notices up here about facilitating the question discussion period.
Thanks, Leema, and everyone. It is now time for our first question break, but before we get to that, I wanted to remind everyone, and for those who might have joined us a little bit late, that you do have the option of turning off notifications of others joining us simply by following the steps there on the screen using the edit menu and then following that chain down. Or if you're a Mac user, just simply click on Blackboard Collaborate at the top of your window there. You can also minimize or detach and expand your chat panel by using either the arrow on the left or the menu there on the right of the chat window. And I also encourage you to check out the NSTA community forums to continue the discussion after this evening, and the link is there in the chat window. And now we'll go ahead and advance to our questions slide. We look forward to hearing what you'd like to know about the content that our presenters just gave us. So please do go ahead and type your questions there into the chat, and we will pull out some of those for Kate and Leema to respond to.
Great. We've got right up here a question from Kathleen about do you have any recommendations in terms of assessing students' facility with constructing explanations and designing solutions, either in a formative sense or in a summative sense?
I think that's a really interesting question. I mean, we're going to move into examples next, and I think you can assess them either in terms of talk or writing in a variety of ways. I think they can be more formative in the sense that, it's not necessarily that you're looking for a final product in terms of the end of the unit. It could be an explanation they're constructing at the end of an investigation you've done in class, or you're having them develop a design solution that they're actually going to go through multiple cycles, and you want to assess kind of a part in the middle. So you can either look at the actual writing and or product that they're producing and use rubrics to score it, or you can also do something even more informal in terms of the discussion that occurs in the classroom. And I think one thing we're going to talk a little bit more about is the teachers that we've worked with. It seems like there's a real relationship between the language that you see in the classroom discussions and then what you see in the students' writing, that helping them use this kind of language in class really supports them in their actual writing. So if you want them to be justifying the explanations that they're producing using evidence, that during classroom conversation, you want to see that there as well, where you as the teacher are asking questions like, what is your evidence for that? And then you see it in the students' talk and then subsequently in their writing. So we're not actually going to present any rubrics today, but at the end, Leema and I, we're going to put our email up. If you are specifically interested in a more formal rubric, definitely feel free to email me, and I have some that I'd be happy to share. So I think you can do something more formal, more summative at the end of a unit in terms of looking at the writing or product, or something more formative as well. Now, Leema, I don't know if you want to add on.
No, I think that covered it. I think I will say that in engineering, there's an idea that multiple different solutions might attack the problem very differently, and so we think about weighted rubrics that, you know, you've optimized for this constraint or criteria and possibly not this other one, whereas another group may have done it the other way. And so the use of rubrics becomes a little bit more nuanced in that way, and helping the kids think through those problems is an interesting aspect from the engineering world. But yeah, that would be my addition.
Great. I'm going to interject with a question of my own. In your diagram was about relationships between the different practices. Things ultimately fed into the explanation category. Do you see situations also where the development of constructing explanations, designing solutions, all turn around and feed into the other practices and lead into those?
Definitely. We made a simplified model to emphasize that one point, but as we learn more about the world and can explain it in more and more ways, that leads to more generalized knowledge that might fit more in the modeling, constructing a model practice, and that more theoretical knowledge is going to then guide your next round of questions. In addition, as you're developing an explanation about this phenomenon that you're observing, it's going to raise more questions, and so everything you're doing would cycle back without a doubt. Kate, would you agree with that?
I do agree. I mean, we played with that diagram for a long time. You know, I think you can just have arrows pointing between all the practices in all different directions because they are very iterative. They work together. And I think that's one of the things that makes science so interesting, right? Like, science is not just the set body of facts. It's a way of thinking. It's a way of knowing. It's a way of reasoning. We want to get kids engaged in these practices, and they're doing them all to make sense of the world around them and to design these solutions. So I think it's a tricky thing about both the frameworks and the next generation science standards. You have these 8 practices that we want to separate because they are distinct, but at the same time, they work synergistically, and they're very much related to each other. So there's a tension. You don't want to make them too discrete because you kind of lose an essence of what science is, because science is all of them. But I don't think you can give kids all of these things all at once in terms of instruction, because that can be confusing for them. So there's a tension there that I think is hard.
Sort of quickly building off of that and keeping in mind that you guys weren't part of the framework writing committee, but Ashley is asking, why are practices 6 and 7 separate practices if they work together? Should teachers think of them as one practice? Who wants to take first shot?
I don't know what the framework people were thinking when they did it that way. I believe one reason to have them separate is because argumentation, while it's emphasized around explanation, and we often, like I said, see it as a single product, we also want to be arguing at other points in the process. We want to be arguing about what sorts of methods are appropriate for answering the question, or do we think this is the most appropriate model for understanding the particulate nature of matter, or various things like that. Argumentation can happen around most of the other practices, and so it's important to call out separate from explanation.
Great. So I think we're ready. Then we can move on to the next part here, and we'll have some more questions in a little bit.
That sounds great. So we wanted to move into some student examples, and we're going to talk about student challenges. But before we illustrated them, we want to get a sense of your own thinking. So what do you think will be hardest for your students? So if you're going to engage your kids in developing explanations and developing solutions, what do you think would be hardest for them? So choice A here is considering multiple explanations or solutions. This is the idea that students sometimes just zoom in and focus on one idea or one solution, right? They have one explanation in mind or one solution in mind and don't consider the other ones. B is using evidence to support their ideas. Okay, maybe they'll put a claim out there, maybe they'll put a solution out there, but they won't actually use the evidence to support it. They won't back up their thinking. C, explaining why their evidence supports their ideas. So, okay, maybe they'll give you evidence, but they won't tell you that link. They won't explain the connection between their claim and evidence in terms of the justification. Or D, revising explanations and solutions based on new evidence or scientific knowledge. So here the idea that they develop an initial explanation or they develop an initial solution, and then you end up getting more data. And when you get more data, it actually alters what the explanation or the solution should be. And that students can have a hard time with that. Sometimes they just pick one thing and stay with it. They don't actually revise over time. So seems like we have quite a bit of variation here. We'll give you another minute for folks to select their choices. Great. Bryn, would you mind putting the graph up again first?
Sure. I'll go ahead and lock the poll and then put up the graph.
This is really interesting. So C seems like the most common. So explaining why their evidence supports their ideas at 39%. And then we have split between A and D. And I think A and D are actually kind of related, right? A, considering multiple explanations, and D, revising explanations and solutions based on new evidence. And then it seems like B might be the easiest for some kids. That some people think it's challenging, but this one was not selected as frequently. So using evidence to support their ideas. Really interesting. We can't do it since it's a webinar, but I would be curious in terms of what grade level people were thinking, right? So I could see that some things might be easier or harder for elementary students versus middle school students versus high school students. And that as they get older and they have more experiences, some aspects are easier for them and some aspects still continue to be challenging. So we're gonna show you some examples to illustrate what these practices look like. We selected a number of student examples. So these are examples from the teachers that Leema and I work with. They were obviously examples that were created in classrooms before the development of the next generation science standards, since these are still in the works. But we think they align very closely with how the standards talk about both explanation and solutions. So we picked some different examples in order to illustrate across the grade levels, as well as to have examples of both explanations and solutions. So we're going to start off by looking at two elementary level examples, one being a lever explanation and the second being a motion solution. Then we're going to move into two middle school examples, one being about air and an explanation, and the other being about natural selection and an explanation. And then we're going to move into a high school engineering solution. And after we go through these different examples and talk about them a little bit, we'll kind of summarize what we and the teachers we've worked with and other people in this field have found can be really challenging for students around these practices. So in terms of an elementary example, this is from a 5th grade teacher that I've worked with here in Boston, and he was having his students engage in a unit on simple machines. So specifically this was during a section of the unit focusing on levers, and one of the things that he had found is that his students tended to think levers always make work easier. So they had a difficult time with the idea that levers are easier or harder depending on the position of the fulcrum. They kind of just thought if you use a lever, it's always going to make work easier. So he posed this question to them, does a lever make work easier? He had the kids do a number of investigations around it to try to help them understand this phenomena in more detail. And then he asked them to write up an explanation at the end that was pulling from data from the different investigations that they had done. So what we did here, the orange is the evidence that the students used to support their explanation. And then the black is really getting into the how or why this phenomena occurs, so understanding how levers can actually make things easier. So what the student here wrote was levers sometimes make work easier, which is what the teacher was hoping the students would end up with by the end of the investigation. The student then goes on and provides some evidence. When we picked up the load without the lever, it was 2.2 newtons. When the load was 5.0 centimeters from the fulcrum and the effort was 10 centimeters from the fulcrum, it was 0.8 newtons. So, and then continues on providing some other evidence. But the teacher wanted the kids to specifically use data from their investigation. So they have the newtons in here illustrating times when it was easier and when it was harder from what it was like to pick up the load without the lever, which was the 2.2 newtons. And then after the evidence, again, kind of going into this idea in more depth in terms of how levers make work easier. Doing work is the ability to move an object. If it takes less force, the work is easier. A lever can make work easier depending on the position of the fulcrum, effort, and load. When the fulcrum is close to the load and far from the effort, the work was easier. So going back to before we talked about explanations, you have these two aspects going on, the how or why a phenomena is occurring, and then using evidence to support that. So here's another elementary example. This is from a different elementary teacher that I've gotten to work with here in Boston, Nick, who is fabulous. This is an example that he actually just recently created. So I don't have actual student work to show you. He's going to use this as an assessment. So I'm going to explain to you what the assessment is, and then he kind of mocked up what he's hoping the kids will end up doing. So this is from a 4th grade unit he's using with his students, and they're building these Connect vehicles. So they do a number of investigations throughout the unit where they're design challenges. They're designing these vehicles and they're testing different aspects to see how different things impact how far the vehicle travels. So they do things like putting blocks on it to see how changing the load affects it, changing the wheels, this thing kind of sticking up in the middle, that's the sail. So using these different aspects, so this here is the sail, and seeing how they affect how far the car travels. So they do all these design challenges, they collect data, and then he's planning on using this as an assessment at the end. So he's going to ask the kids this question, can you make this Connect vehicle travel farther? And he gives them these images here. Some students build this Connect vehicle, and he wants them to think about what they learned and all their own designs and investigations and apply that to this particular design. So he's hoping that the students will have a response such as this one. So yes, I could redesign this Connect vehicle to make it travel farther. I will explain 3 different changes I would make to this vehicle. First, I would take off all of the extra blocks that aren't doing anything to help the vehicle stay together or move. I know this will make it go farther. And then in orange, again, we highlighted what he's looking for in terms of evidence. So like I said, they do a number of investigations throughout the unit, and he's hoping they use some of the data from those investigations to support their decision around the design solution. So in science class, when our standard vehicle was carrying 2 blocks, it only traveled 10 centimeters before it stopped. When it wasn't carrying any blocks, it traveled all the way across our table, 120 centimeters. Both times the same force was pulling on our vehicle. So connecting specifically to the data in class in order to support their decision around this. And then going on in black, explaining why this makes sense. This makes sense because when something is heavy, it needs a lot of force on it to make it move. If you take off those extra blocks, it will need less force on it to make it move. So this is one of the 3 changes he has hoped they will make, and then he goes on to articulate the second and third as well. So in this case, this is something that he's thinking more of in terms of summative, that he's hoping that they'll do at the end of a unit. This next example here is from a middle school teacher that I work with in Boston. And I picked this example because the structure is a little different, and I find that interesting, and I thought it might be useful to share. So in this example, Liz created this question, and the question is, what is air? So her middle school students did a number of investigations around air, and she's hoping that they're going to basically understand at the end that air is matter, and that they'll use data from these different investigations that they've done in order to support this. Now, when she brought in a bunch of samples of work from her students doing this, and one of the things that we agreed was interesting about this is how they kind of structured it. That they have this initial claim, air is matter, They provide some evidence, and then they explain why that evidence supports their claim. So kind of what we talked about before in terms of their reasoning for why it supports their claim. And then they provide some more evidence, and afterwards, again, a little bit of reasoning for why that supports the claim. So the structure is a little different than I think what she was originally imagining that they would do. Originally, I think she thought her kids would write more, claim all of the evidence, and then explain after all the evidence why it supports the claim. But in this case, I actually think it makes sense what the student chose to do, as did Liz. It just wasn't what she was expecting. So the claim is air is matter. The first piece of evidence, I think air has mass because in the balloon experiment, when we were comparing or weighing the deflated balloon to the balloon filled with air, the balloon filled with air weighed more. This is because of mass. Mass means the amount of matter in something. The balloon which had air in it has more mass. So that's specific to that piece of evidence around balloon. They then go on and provide some other evidence from a different experiment. Another reason why I think air has mass is because in the syringe experiment, it was difficult to push the top of the syringe because the air was blocking it from going down. So that's their observation from that particular experiment. They then go on and explain why that data connects to their claim about air as matter. The tiny little molecules were trapped in a small space and creating more pressure. Air pressure made it difficult to push down because the air takes up space. It is made of matter and has mass. It is true that air is made of matter and has mass. So again, another example here in terms of explanation, getting at how or why a phenomena occurs. This phenomena here is what is air. And again, we want to see in their explanations that they're using evidence to support their ideas that they're developing. Leema, I think this one is you.
Leema, did you turn your mic on?
Uh-oh, I just got a text from her on my phone that says her mic is broken. I don't know if, Jeff, you can give her any technical support here. I will start explaining. Oh, her whole system is frozen. Okay. Well, while she is doing that, I will explain her example, though I probably won't do it quite as well as she would. So this is another middle school example. This is from a unit that's focused on natural selection. And the question the students are answering is, why did most of the finches die in 1973 and some survive? So in this case, the students were looking at a whole bunch of data around this through an online system, and they were trying to come up with different claims around it. So we picked this example to share because it's an example of talk. And the other examples of explanation that we've had so far are students' written explanation, but we wanted to illustrate that explanation is not something that just happens in writing, but it happens in talk as well. So here what you see is the first student, this is during a little discussion they're having as a group, the first student, Janelle, says, what I notice is that your claim and our claim are opposite. Another student, Toby, says, yeah. Janelle says, because we say it's from the drought and you say it's from harsh rain. Toby says, yeah. And Janelle says, and our evidence from that is that we actually have measurement that says the rainfall decreased. Do you actually have numbers that say the rainfall increased? So Janelle's seen this difference, right? They have opposite claims, and she provides evidence for why she thinks her claim is correct, and she asks Toby about his. So Toby now responds, yeah, and Janelle says, because you can't say it increased without numbers. Toby says, yeah, and Janelle says, I want to see it. So she's pushing for the evidence. And as we talked about before, you know, I very much think what you see in the talk is going to be related to what you see in the writing. So what you see here is these students are talking. They are eventually going to write something, but they're having different claims, and they're debating those different claims and where they came from and what evidence they have to support it in terms of this phenomena of why the finches died in 1973. So the conversation goes on. Toby says, okay, so the rainfall in 1973 seemed pretty devastating to kill all the finches in the wet season. Janelle says, but here's the thing, the rainfall is pretty balanced. And Toby says, no, I mean, it's not. It's not just going to keep going up, because I remember in 1979, none of the finches really died in the wet season or the dry season, and that's his evidence. So he's taking some data from a different year and articulating why he sees that as evidence for his claim. Janelle then goes on, but the rainfall, I don't think it kills the plants. I don't think it drowns them at all. And Toby says it does. That's what my mom says, that if it rains too hard, that it drowns the plants so they can't survive. And Janelle says, I know. So this is another example similar to the ones that we've been sharing before, where you see kids trying to make sense of the world around them. In this case, it's a world back in 1973, but they're still exploring this world through an online system, trying to make sense of this data, construct claims, and then use evidence in order to support those claims. Looks like Leema is back again. I don't know if she's still trying to get restarted.
It looks like it's working again. I'm sorry about that.
Yes, we can hear you.
Excellent.
So you just missed it, but I just explained your natural selection explanation here, probably not as well as you would have, and talked about how we wanted to illustrate an example in talk as well as in writing. I was done talking about it, but I don't know if there's something you want to add about this one. I know you probably missed what I said.
Yeah, I have no idea what you said, but I'm sure that you covered it fabulously, so I'm happy to move on. I'm sorry about the technical difficulties. The other example that I was going to talk to you all about comes from a high school class that I've been working with here in Austin, and it's actually an engineering class. And so we wanted to use this as an example of a high school solution. In this particular case, the students were designing pinhole cameras, and I'll show you an example of one in just a minute. I wanted to show you two things with this example, and one is how it's based in evidence, similar to the explanations. And so the orange here is highlighting the students' evidence or data about whether or not they've met the success criteria. In this particular case, they are in the middle of creating their pinhole cameras, and they're trying to make their boxes light tight, which was a huge challenge. All of the students ended up with completely black film paper, meaning that, you know, the light flooded the inside of their cameras. So they were working on this, and you can see through this explanation the ways that they fixed it and that they tested it 3 different times. The 3 different orange sentences are different iterations of the test, and they talk about adding tape around the edges and various things like that, sealing all of the open edges. And so this is an example of how you might see a student talk about their solution and its relationship to the evidence they're collecting in an engineering process. I wanted to show you other examples of solutions because, of course, in the engineering world, we could have solutions like that paragraph, or we could have things like this. And so the students at different points in their process were designing sketches or drawing sketches of the cameras they wanted to build, and then they physically were building their pinhole cameras, which is the picture on the right. In this case, that flap is the pinhole, and that's how they'll be able to actually let the light in when they want to take the desired picture. So those are all of the example solutions that we had or example solutions and explanations that we had to show you guys. We started this section talking about the different challenges that occur as we're supporting students in this. And as Kate said at the very beginning of this talk, designing solutions and constructing explanations is very challenging to do in classrooms for various reasons. And I think based on the poll that you guys did a little bit ago, these are all challenges that you are well aware of. So things like using evidence to support their ideas. There's a lot of work out there that says that this can be hard for kids and for adults, actually, that we're much more likely to draw upon our own opinions and actually have a difficult time using sufficient evidence to support our ideas. Related to that, once we have the evidence, explaining the connection between the evidence and the explanation. So not just stating it, but providing that justification or the link. And considering multiple explanations or solutions, we have a tendency to very much focus on one idea, and again, this is cross age spans into adults, and it relates to the challenges around using evidence to support an idea. We can kind of cherry pick the evidence that supports the one idea that we want to be supporting, which then leads to challenges around revising explanations and solutions. So these are all aspects of these practices that can be particularly challenging in the classroom. And so we wanted to move on to the next section, which is going to be around designing learning environments or activities and supporting the kids in these challenges. But first, we wanted to have an opportunity to talk about some your questions and thoughts around these examples. Bryn?
Thanks, Leema, and glad to have you back. Thanks for bearing with us through your technical difficulty. For everyone else, I'd like to remind you that before we get to your questions, you do have the option of turning off those notifications of others arriving, and there's the steps to do that. You can change the size of your chat box to make it larger or smaller for your preference. And of course, do continue the discussion there in the community forums in the NSTA Learning Center. Now we're going to move on to your questions about what explanations and solutions look like in K-12 classrooms. The chat window is now open and ready for your questions and comments.
All right, and so folks here can put some questions up here in the window. My first one here is a logistical question. How do you go and record a conversation, or do students write it out, or do you record it and then type it out? And I don't know, this is both, I assume for your research in some cases you're recording things, but in terms of how you would think a teacher would be engaged in doing this, what would your recommendations be?
I can start, and Leema, you should feel free to add on. So, I mean, from a research perspective, obviously that's different. Leema and I tend to be in a room videotaping. But I've been doing some professional development with teachers in Boston. And we met last week, and one of the things the teachers wanted to do was to share with each other some of the discussions that they were hearing in their classroom. So a number of the teachers had flip cameras, and they were using those to record, and then they were bringing them in and just picking short sections, like 2 to 3 minutes, that they were sharing with their small groups or transcribing to try to get a sense of what some of the challenges were. I would say that was more formative in terms of trying to come up with challenges so they could better design future lessons. In terms of more of an assessment, the other thing that we've been working on, I don't have something concrete to share yet. Hopefully I will, and when I do, I'd be happy to share it. But what I've been working on with the teachers is we've been trying to come up with kind of a checklist that they can use during class discussions, something that, you know, is easier and more on the fly, because you don't have the time necessarily to always be videotaping and then transcribing a little section of your classroom because you're incredibly busy. So they were looking for we're trying to develop some kind of tool that they can use to get a sense of what ideas are they hearing from their class as a whole, or something that they could use to look at specific groups. Leema, I don't know if you have suggestions.
No, that second suggestion is exactly what I was thinking, that the transcript that you guys saw came from research. It didn't come from a teacher solely for the teacher's practice. And given time constraints and concerns, I would be thinking more along the lines of post-class reflection notes that the teacher could take, or even better, the on-the-spot checklists that Kate was talking about. I think that that's a more realistic way of capturing and thinking about class discussions and how the explanation is happening in them than video recording and analyzing that through transcripts.
Do you ever, for either of you, do you ever have your students critique each other's ability to develop an explanation?
Yes, in my work, it's a big part of how we construct explanations, and it's part of why explanation and argumentation are seen as so linked. That having, and this will come up more explicitly in the next section around classroom practices for supporting explanations. But having small group conversations and ways of supporting the students in engaging in that critique can be a really powerful way of helping the students improve their explanations. It in and of itself has challenges, and I think that when the week on argumentation will also be focused on some of those challenges, I would think. But it's definitely an important aspect of it.
I've also had students critique each other's, both in writing and in talk. In terms of talk, I have a checklist that the teachers have been using with their kids during talk, and we've been using that as a starting point to help the teachers develop something for themselves that we're playing around with. Like I said, we just started doing this, so I don't have something great to share. But for the students, we have them evaluating each other's explanations with different aspects. So evaluating it in terms of, are they using evidence? Are they articulating why their evidence supports their claim? Are they considering multiple different explanations? Are they articulating why one explanation is stronger than another? So they were using this while they were listening to each other in order to try to help them think more critically about it, and then use it to then help them as they questioned each other. And in a different way, I've also had kids critique each other's written explanations where they've traded with a partner and identified and critiqued different aspects of it. So things like where they trade with another student and they have to circle the claim and number the pieces of evidence and then underline the reasoning and then provide the other student with critical feedback in terms of how could you help improve this written explanation.
Great. We've had some folks who are asking about particular slides in the PowerPoint and looking at and seeing those. I've put down the link to the PowerPoint you can get to if you want to open it up and take a look at something. So moving around here on the main screen is a little bit tricky. But another piece here that's been asked about is, how important is it for teachers to model these processes of explanation? If you guys would like to comment on that.
I think it's incredibly important, right? I mean, I feel like a lot of how students learn how to do these practices is by learning from the teacher in terms of what he or she is doing. So in terms of being explicit about the practices that a teacher is using. So not only just doing it, but kind of like a think aloud, right? Explaining what they're doing and why they're doing it and really providing that rationale for the students. And I was looking at a couple days ago, one of the teachers, Nancy, that I work with in Boston, I think she does a really nice job with this and is very critical of herself in front of the students in a constructive way that I think is helpful, right? She'll say something like, so the initial explanation I had in terms of she was doing plate tectonics and the movement of the plates. So the initial explanation I had about how the plates have changed is this, but now we have this new evidence, so it makes me realize that my explanation didn't include this concept. So she kind of not only does it, but also shows how explanations can change and how new evidence can do that. And I think that really helps the students to have that model that they can see to use in their own language in both talk and writing.
It seems to me, I'm going to introduce a second here, and maybe then Leema can fill on this. So there's two different ways that an explanation can be problematic. One is that it hasn't, that new evidence or things come to light that it hasn't incorporated, and there's also sort of the aspect of a breakdown in logic or just a general form of mixing fact and opinion together. Do you treat all those things as just different issues, or are just problems that need to be dealt with, or do you find use in categorizing the different types of issues that can come up?
So we've definitely talked about or worked with classrooms to help the kids think of different criteria for their explanations, and often this comes in the form of, question stems or things that they would think about when evaluating other people's explanations. And so in that, the categorization is really important because we want to give students a range of potential pitfalls to be looking for. So definitely thinking about it at that sort of grain size is really helpful for, again, supporting them in critiquing it entirely and not focusing on just one aspect of it.
All right, and one very specific question here, it was Deborah asked, do you think there's any preference between having students write in first person versus third person in the development of their explanations?
That's interesting. I don't personally have an opinion there. I don't know if, I have no idea if Leema agrees with me or not. I want to see the ideas. So I want to see that they're making a claim. I want to see that they're bringing in evidence to support it. I want to see that kind of logical coherence that I feel like Ted was bringing up before. But I don't personally have a strong preference of whether or not, they're writing, I think that the plates moved here, or if they're just saying the plates moved. So whether or not they're doing it in first or third person. Leema, I actually don't know what you think.
It's a fabulous question, and we've never talked about it. I'm definitely of two minds. It's really important to me that the students have an opportunity to feel ownership over the ideas, that they're constructing the ideas and they're defending their own idea and maybe trying to persuade their classmates of that idea. And from that perspective, you would think that first person would be a really useful way of communicating that sort of ownership. On the other hand, argumentation can get heated, and we want to help the students think about arguing about the ideas, not arguing with each other, and the first person can maybe blur that line a little bit. So I haven't seen research, and those are my two minds on it, and I would love to think more or see more, but that's
Great, thanks. That's very useful. Why don't we head on through here, and we still have some time for some questions at the end.
So we have one more poll. We wanted to have an opportunity to think about or to see what you guys were thinking about with respect to why or how this would be hard to fit into your own classroom instruction. And so the options, as we were thinking about our own experiences with teachers and what they've been telling us, things that we're seeing as challenging is finding places in the curriculum where it makes sense to do explanation, possibly developing questions that help focus students on using evidence when they're constructing explanations or designing solutions, supporting the discussion, and then supporting the writing of these products. And so we're curious to see which of these you guys think would be most difficult in your classrooms. This is much more evenly split than the other polls were. It's really interesting. It's slowing down. Bryn, could you help us with the graph? Oh, it's not quite done.
Sure, we can give just another moment and then I'll lock and publish the graph.
Thank you. Thank you, Bryn. So yeah, as you can see on this graph, that it seems that all of these possibilities are things that are worrying you as you think about supporting these in your classrooms, and that makes a lot of sense. Like I said, these options came from experiences we've had and conversations we've had with teachers around supporting them. So we're going to talk about some strategies we've been working with teachers on for supporting students in these practices. And the three strategies we're going to be talking about is the development of good questions, and then we'll talk about supporting the class discussions, and finally the student writing. So hopefully we'll address a lot of the challenges that you guys are considering through this conversation today. I'm going to start with number 1, talking about how we develop good questions to support explanations and solutions. So a good question, in quotes, and by this we mean a question that can inspire the rich explanations like the examples that you guys saw. So going beyond questions where the students describe what happened, and instead they're actually constructing a claim, answering a bigger question. And so the things that we're looking at, the criteria that we often give teachers as they're thinking about developing these sorts of questions, is that there needs to be data, that you need to be able to identify data that students could use as evidence to support their claims. It also needs to connect to scientific principles or the core ideas in the language of the framework that the students can use to make sense of the data. And this is a challenge, in my experience, particularly in the younger grades. We'll see a lot of really great explanations that use the kids will have a claim and there's evidence to support their claim, but it doesn't connect to a scientific principle. It doesn't have them explore the actual science ideas, and so this criteria comes from those concerns. We also want to ensure that the questions have multiple plausible answers. To have the kind of rich conversations we've been talking about, and to motivate the support of their claims with that evidence, they need to have a reason to do that. And multiple plausible answers provides that reason. If there's the possibility of disagreement, then you have a reason to have to support your claim. In writing the question, we have to worry quite a bit about clarity. This comes out throughout all of our work with teachers. Is we think this question, we know what this question means, and students take it in completely different directions. So we wanted to give some examples of what this looks like, or what questions that have challenges with these criteria might look like. So lacking clarity, what will happen when you mix salt and water? You can imagine students describing the salt disappearing. You can imagine a student saying, you know, the water will turn salty or turn into a mixture, without really understanding exactly what is the science idea that you're hoping to get the kids to be thinking about. Lacking evidence, these two examples, the first one, why is a diamond a mineral and not a rock? It's a definitional question, right? It's pushing hard on the science definition, so it's connected to those core ideas, but there's no real evidence that the kids can be gathering to answer that sort of question. And lacking scientific principles, does a paper airplane fly better or worse with a snub nose? So in this situation, I've seen student answers where they say, you know, well, the pointed airplane flew further, and so it flies worse with a snub nose, but they aren't thinking about what's happening with the air and how that's working, because the question doesn't inspire that more deeper thought. So more successful questions are ones that ask students to use evidence to support their explanation or solution. So for example, what bird beak is the best adaptation for this environment? This question is asking students to use evidence from their explorations and an activity where they were pretending to be different bird beaks. And you could imagine them making a claim like, well, the slotted spoon is best in the sand environment, for example, because of this evidence that I have. And that makes a lot of sense because we know that a bird with this shaped beak needs to eat this kind of food. And you can see it going further into the science and not just the observation. And each of these examples are similarly provide opportunity for students to think about the evidence and the science in defending their claims. Kate, you want to talk about the next ones? Yep.
And just to add one other thing about the questions, it is not easy to develop a good question. I feel like I've been doing this for, I don't know, 10 years now, trying to develop good questions, and I develop bad questions all the time. So those good and bad questions we shared were ones that actually came from work that we've been doing with teachers. So sometimes you develop a question and you think this is great, and then you actually try it out in class and the discussion doesn't go where you think it's gonna, or you collect the students' writing and they answered in a completely different way. So these guidelines kind of came from that to help us think about it, but it's one of those things that takes time and it takes practice, and you can try a question and then end up really needing to revise it in order to help it be a stronger question to help the students. So another thing, and we really have already touched on this quite a bit, is this idea of talk moves or classroom culture. And it seemed like from the poll we did earlier that people felt like the discussion might perhaps be a little bit easier for their students than the writing. But the idea that helping them in the talk can then help them in the writing, and we want to try to engage them in both modalities, in both the talk and writing in these types of practices. So we want to help orchestrate the discussion, support students in communicating their ideas, making their thinking visible so it's not just in their head but actually out there, which can enable us to better assess their understanding and get a formative sense of where the instruction needs to go. These are some examples of specific talk moves from a National Research Council publication. I don't know if you've seen it before or not. It is sitting next to me on my desk, but you can't see it because you can't see me. So it's called Ready, Set, Science, Putting Research to Work in K-8 Science Classrooms. It is focused on elementary and middle school classrooms, but I have used these questions with high school teachers as well who feel like they are very successful for their students as well. So just some examples of the kinds of questions you can ask to push students to really articulate their understanding in terms of how or why a phenomena occurs, as well as to encourage them to justify why they're thinking that and to really push on that. So these questions aren't specifically focused on explanations and design solutions, but can encourage students to really think about and articulate their reasoning. This next set of questions comes from some work I did with a colleague, Carla Zembasal at Penn State, which are more focused specifically on explanation. So they were developed to help kids in creating evidence-based explanations using a framework that we've used in some of our work that focuses on claim, evidence, and reasoning, the reasoning being the idea of how or why the evidence supports the claim. So these are just some examples of questions, again, to help kids during the discussion. The first one, refocus on the guiding question. The students, particularly younger students, can get off topic on occasion. So trying to encourage them to come back to whatever the overarching question is that you're trying to answer. So those questions that Leema just shared. Next, looking for patterns in the data. You know, really, this goes back to the idea before that these 8 different scientific practices are very much linked. So in order to use evidence to support an explanation, you need to be making sense of the data, and kids can need help in that and to help them with that. So what patterns are you beginning to notice in your data? The next is really pushing them to actually make a claim. What claim can you make based on the data that you have so far? So what is your initial explanation here? What do you think is going on? The next one, considering alternatives, so bringing this idea of not just one claim or one explanation, but considering multiple. Is there a different claim that explains the data better? Are there other possibilities that we want to consider? And trying to get kids to move beyond just focusing on one. And then this idea of predictions as well. Given your results so far, what do you predict will happen next? So thinking forward, thinking about the explanation you've constructed so far, the evidence you've used to do that, what do you think will happen next in order to push them in applying? And again, connecting to some of these other practices. As we talked about before, they are very much integrated and synergistic. This is an example transcript from a 3rd grade classroom that Carla Zembasal, who I mentioned before, was working with. She was working with a teacher there, just to kind of show the kind of questions that the teacher was integrating. So here the class was answering the question, how do pulleys help us do work? And the teacher had posted 3 claims up on the board, A, B, and C. And she wanted students to decide which one was the strongest explanation. And one student says, Jordan says, because if people didn't know the distance part, then they wouldn't pick A, because distance and decreasing the force, they both seem to go together. And the teacher's pushing on this. How do you know that? And Jordan says, because when you decrease the force, there's more distance, and when there's less distance, there's more force. Again, the teacher comes back again, but I'm asking you, how do you know that? And Jordan says, because of all the experiments we've done. And the teacher, what did you do to know more about distance? And Jordan says, I know about distance with levers. And you know what I think is nice about this is that this teacher has developed a very strong classroom culture where questioning is accepted. Right? Where if you could watch the video, which we didn't want to show you because we didn't want to freeze the system, but if you watch the video, you can see that Jordan is very open to keep going. Right? She doesn't initially explain it to the extent that the teacher wants her to, but questioning and this justifying and using evidence is part of the classroom culture. So the fact that the teacher keeps questioning her is kind of accepted, and that this is what happens. We really question each other and try to push on these ideas. So the last strategy we wanted to talk about a little bit is scaffolding student writing. So if students are writing their explanations or writing up about their design solutions, how can you help them do this, and how can you really help them with the justification piece? Writing scaffolds can take on a variety of different forms. They can be sentence starters, questions, or other prompts that give them kind of hints about what to think about as they're doing this. When we develop student writing scaffolds, we consider some different characteristics. So first, this idea of content and general support. A general support would be something like, remember to include evidence, which is data from our investigation. That's a general prompt I could give a student that they could use across a variety of different explanations. It could be about biodiversity, chemical reaction, plate tectonics, and that general support would still encourage them to include evidence. A content-specific support is actually getting into content, like helping them understand what counts as evidence here. So, for example, if I reminded them in the prompt, remember to use evidence that includes measurements around force from our lever investigation. So it actually is specific to the investigation and trying to help them understand like what counts as evidence. Next thing we consider is the detail and the length. So on the one hand, more detail can be helpful because it gives them a better sense of your expectation. On the other hand, students are only going to read so much, so you don't want to make it so long that it's overwhelming. So keeping that in mind. And this last idea around fading. That is, as students have more practice with this and develop more expertise, they may need less support. So over time, you might not need to do something like define what counts as evidence as they develop a stronger understanding. So this is an example. This is one of the successful questions that Leema shared before. Which bird beak is the best adaptation for this environment and why? And here is an example of some writing scaffolds that the teacher I was working with developed for this. There was more space on the actual student sheet so they could write, but just so you could get a sense of it on one slide. So he reminded them for claim, write a sentence stating which beak is the best adaptation for this environment. Evidence, provide scientific data to support your claim. That part's kind of general, and then the rest is specific. The evidence should include the amount of food, marbles, pennies, popsicle sticks, and red water that the beaks ate. And then the reasoning, explain why your evidence supports your claim. Again, starts general, but then gets specific. Describe what an adaptation is and why your evidence allowed you to determine the beak was the best adaptation. So, I think these can take different forms, but especially if this is something new for your students, having some kind of written reminder on the page can help them understand what to include in their explanation or solution. So just to kind of summarize across what we've been talking about, and then we'll give you time for some more questions. This idea that in the next generation science standards, there's this focus on both explanations and solutions as the products. And explanations being how or why a phenomena occurs, and it relies on evidence. Solutions in engineering being the solution to a problem, and that selection is based on multiple criteria, including evidence. I think from both Leema and my work, we feel like there's many opportunities to engage kids in these practices. They just show up everywhere in science and engineering instruction. It can take time to figure out where the best places are, but there really are a lot of possibilities out there in your existing curriculum to help them do this. But it is challenging. So the first time that they do it, it is not going to be perfect, and they're going to need support. And there's a variety of different ways that you can provide them with support, and we've talked a little bit about some of those. So I wanted to give you this as well. As I mentioned before, we'll have some time for questions, but if there's specific resources that you're looking for or something that you feel like Leema or I could help you with, definitely feel free to email us. I put my website up here too. There's some links off of it to some resources that I've been developing with the teachers in Boston, which we just put out there to share with other folks I'm happy to have other people use them as well if they are useful for you. So last time for questions.
Thanks, Kate. And in the interest of time, I think, Ted, perhaps we'll just take maybe one question before moving on to your final portion and then our evaluation. So everyone, just a few reminders up there on the screen. Of course, continue the discussion with us in the community forums. We'll turn the chat window on now for just a few moments, and we'll take one question at this point, and then after we finish up, we'll answer any additional ones.
There's a chance to see who types the most quickly. And we may have satiated everyone's point here. I mean, I think we've got some folks asking about the website. We'll get that to you all. I think the emphasis is points that you've made here about that this is something that it takes real work to do, and I think the next generation science standards overall are going to require, some major time for teachers to get a sense of, to figure out how to implement in a successful manner, and they should be expecting that there are going to be some stumbles along the way and not let that get in the way. I'm assuming that the teachers you're working with, while probably struggled at first, have really found, once they've gotten through that situation, it to be a very rewarding way of going about investigating. Would that be accurate?
I think it's a challenge, and I think it's something, like you said, that as people start working on this and talking to others about it and seeing what their students can do, it's something that you get more comfortable with. I mean, kids are still going to have challenges, right? So you're not going to come up with the perfect way to do it after trying this for a month. But I definitely feel like teachers get more comfortable and figure out different strategies for their particular students in what works better for them and is harder.
But I'd also like to underscore the rewarding aspect of it, that it is incredibly challenging, but it creates an opportunity for teachers to see their students thinking and reasoning in ways that that classroom practices that don't incorporate explanation can sometimes cover up.
Great. So we're going to go on here just to point out some places people can get some additional information. People will then have a chance to fill out the survey. And after that, Leema and Kay will be willing to stay for a couple minutes more to answer any questions that come up through there. And so I just want to point out that the place to find up-to-the-date information about the standards is at the NSTA's NGSS page. You can just get to that by nsta.org/NGSS, the website listed right there. You can also find a link to it right on the NSTA homepage. We're slowly bringing out all of our web seminars over the course of this fall. In 2 weeks, we've got Joe Kraychek, who's done work both with Kate and Leema at different points in here, and is well known as actually on the writing team for the Next Generation Science Standards. He'll be talking about engaging an argument from evidence and some information there, as well as his shining smile. We'll go on. As we've mentioned before, graduate credit is available for attending to this. If you're interested in doing that, there's some methods here. You can find information on Shippensburg University's website. I want to point out the community forums around the Next Generation Science Standards. There's a place to continue these conversations. A lot of good information that is coming along, going through here. And we've got the links to the forums put up there for you on the chat window. And coming up in a few weeks, the last conference in Phoenix for the area there. I'll be doing a session specifically on the scientific and engineering practices. Stephen Pruitt is coming to talk about the standards, get some updates on what's going on with all of that, and a number of other sessions. Joe Kraychek, for example, I know has got a session there, and some other people too. And we've got the NSTA Reader's Guide to the Framework. We've mentioned the framework. I also want to mention a guide there that can be a good companion to working with the framework, and that we've been, in all of our journals, having each month articles about the frameworks and the standards, provide some additional information for you all. And with that, we want to thank again Kate and Leema. Turn things over to Bryn.
Thank you, Ted. I would like to thank all of our presenters this evening, Kate, Leema, and Ted, for their time and for sharing all of this great information and material. Everyone, let's use our emoticon button, which is the one with the face on it, and select the applause, the applauding hands, to give our presenters our appreciation. Thank you so much, everyone. And I would like to thank the Carnegie Corporation of New York for sponsoring today's web seminar. And a thank you to the administration of NSTA for their support for web seminars. Here's a look at our upcoming calendar. After Thanksgiving, please do come back and join us to learn more about monarch butterflies and citizen science on November 27th. Then on November 28th, check out the next program in our NASA Explorer School series and learn about distance rate time problems, smart skies. And then on November 29th, join us with the American Chemical Society to look at activities for holiday chemistry. You can register by going to learningcenter.nsta.org/webseminars. I'd like to thank everyone for your participation tonight. We look forward to seeing you again on another NSTA web seminar.